A very general example of that, suppose you have some arbitrary element A reacting with B, and if this is an oxidation reduction reaction, you have element A and an electron is transferred away from element A and is absorbed by element B, leaving element A with a net positive charge because it loses an electron with negative, and leaving B with a net negative. Can you guys see that? Is that good?
From one element.
So that's very general, and also I can't get rid of that, so I'm just going to write over it. It's not a problem. Alright, so in order to keep track of the electrons that are transferred, we assign what are called oxidation states. And what oxidation states are, in essence, they're just an electron bookkeeping method. They don't really have any visible meaning. But there are rules for oxidation states. And the rules are as follows. If you have a pure element, an example would be solid sodium, nitrogen gas, and the reason why that's diatomic is because that's how it's found in nature. Lead, things of that nature. Their oxidation states are all 0. If you have a monoatomic ion, an example would be sodium plus, calcium 2 plus, Cl minus. The oxidation state of the monoatomic ions are identical to the charge on the monoatomic ion. So the oxidation state for a sodium ion would be +1, this would be +2, 2 plus, this would be 1 minus. Oxygen. Always -2 in this class. Hydrogen. Always +1. And fluorine, always -1. Now, again, this all ties into balancing those oxidation reduction reactions. So this will be the first step when you're asked to balance them. So, the key with this is that the sum of the oxidation numbers on any molecule must add up to the total charge on the molecule. So an example would be carbon dioxide. What are the oxidation states? Oxygen, we know, is always -2. So this is -2. And since there are 2 of them, you multiply it times 2, so that's a net charge of -4 that the 2 oxygens contribute. And now, this molecule, does it have a charge or is it neutral? CO2 is neutral, there's no charge here. So the sum of the oxidation states must be equal to 0. Therefore, this must be a positive 4. Carbon must have a positive 4. We do another example. We do phosphate ion. PO4 3-. Now, we know oxygen, again, always -2, but since there are 4 of them, so I'll contribute a net charge of -8. Now, therefore, again, the rule over here says the sum of the oxidation numbers on any molecule should add up to the total charge on the molecule. The charge on this polyatomic ion is -3. Therefore, the sum of the oxidation states of each one of the constituent atoms should add up to -3. This would have to be +1. Is that clear? Make sense? Good. Sulfur hexafluoride. Again, fluorines are -1. Since there are 6 of them, fluorine collectively could be a net charge of -6. And this is a neutral molecule, therefore this has to be a positive 6. Right. So what's the oxidation state of H2? So, now that we know all that, we could go on to balancing redox reactions, which are essentially an abbreviation of oxidation reduction reactions, or electron transfer reactions. The first step to balancing oxidation reduction reactions are to assign oxidation states, which we just did. The second step is to break up the reaction in question into two half reactions. The half reactions are the oxidation half and oxidation means losing electrons. So in the first example that I did with A plus B, A would be oxidized because A loses the electron. General example would be, general half reaction would be X to some arbitrary charge N. Say it loses one electron and we have N plus 1 plus that electron. And for oxidation, the oxidation number increases. So I went from N to N plus 1. N plus 1 is greater than N, so that's oxidation. Oxidation equivalent to oxidation state increases. Then we have the reduction half. And reduction is gaining of electrons. So again, in the example before, B would be reduced, gaining electrons. Again, general kind of half reaction for that. X to some arbitrary charge N gains an electron now, and the oxidation state decreases from N to N minus 1. And reduction is when the oxidation number decreases or reduces. That's where that comes from. So it says reduction is gaining electrons. So if you think of it as reduction, is that the oxidation number reduces. That's where that comes from.
So wait, doesn't that mean when you add an electron it goes down?
So let's do an example of balancing redox reaction. I think this is just a little test. We have lead oxide reacting with ammonia, gas, goes to water, plus hydrogen gas. So what's the first step? Assign oxidation states. So percentage of the reaction, now we have to assign oxidation states. Oxygen is always what? -2. This is a neutral molecule or a molecule with a charge on it? Charge, where's the charge? So this would be
Remove something else.
Is this a neutral molecule or is it charged? It's neutral. We know that hydrogens are always +1, and since there are 3 of them, they contribute to that. +3. Therefore, this must be a nice.
So I'd say NH3.
Great. H2O.
Yeah.
Oxygen is always -2. Therefore,